Okay, everyone, this is Mr. Hinnon. I'm going to try to finish up our little discussion on circular motion. So far, all of our motion has been with a horizontal circle. For example, a car going around a curve, a rubber stopper spinning around something. And as it goes around, there has to be something that's going to provide some kind of centripetal force on this thing. In other words, a force that is pointed towards the center, causing this curve, causing this change in velocity. For an unbanked curve, we know that that centripetal force was just caused by friction. For a banked curve, we know that centripetal force was related to the weight of the object, but then you also had a little bit of a tangent theta, so it's related to the angle itself. Now, however, we're going to get a little bit into, after our last discussion on the orbits of planets and things like that, where gravity is actually the thing that's going to be affected. And so to get into that concept, we're actually going to start off by talking about vertical circles. So we're not going to do circular motion where it's horizontal, like we've been dealing with. We're actually going to be going around in a circle, but now it's going to be vertical. So we're going to actually have points that gravity is going to act in one direction and then points where it's going to act differently. Whereas over here, gravity is always acting downward, and it doesn't affect it as much until we start to get to a banked curve. Barked but banked, where we get a little bit of the weight. Now we're going to actually have a complete situation of the vertical circle. So I'm going to look at an object going around in a circle at four different points. At the top of its motion, at the side, at the bottom, and then another side. So these are all going to be important. As you would imagine, probably the sides are not going to be as important. But if I start off by looking at this object, let's say we're looking at it when it's at the bottom, there are two forces that are acting on it. We know that gravity is going to try to act downward. That's just the weight of the object. And we know there has to be something holding it into a circle. Otherwise, it wouldn't do that. Now, something wouldn't just naturally go around in a vertical circle. So the example I'm going to use is, let's imagine that there is some kind of string that's actually holding this. So imagine that there's a string towards the center. Just like over here, there's a string. Up here, there's a string. All these sides have a string. So as this thing is rotating around in a clockwise fashion, there's some kind of string that's holding it towards the center. So there would also be some kind of tension on that string that we would have to take into account. And so this tension force, I'm going to kind of write it like that. I'm just going to write it as tension. Oops. There is no T in tension. Sorry about that. Like so. Well, the combination of these two forces are what are going to have to provide the centripetal force on this red dot at the bottom. So that's what we're going to be looking at. So at the bottom, what we're going to find is that the centripetal force would equal the tension. I'm just going to call that, actually, I'm going to write this as the word tension completely. And then the weight is actually in the opposite direction, so we would subtract the weight of this object. And the difference between those is what would provide my centripetal force. And then since our centripetal force is mv squared over r, we can set it equal to this stuff. So the tension minus the weight. Usually what we end up doing is we actually solve this for tension. And we show that it's equal to the centripetal force, mv squared over r, plus the weight of this object. So when you are actually at the bottom, you're going to actually find that the tension in the string, or if this was at the bottom of a roller coaster, the force you would feel at the bottom of a roller coaster would be equal to mv squared over r plus your weight. So if you felt a certain amount, if the tension was, say, twice your weight, then you could figure out how fast, if you were feeling 3 times your weight, and so forth. So whenever you go to the bottom of a curve, that's where you're going to have that maximum amount of tension, that maximum amount of force. Think about it, if you're on a roller coaster and you come through the bottom of the curve, that's when you feel pushed into your seat the most. However, when you come around to the side over here, the first thing you notice is now the weight is still pointed straight down, but you still have to have a tension force. But that tension is going to be towards the center of the circle. If that's towards the center, then there is no component of your weight that's actually providing your centripetal force. And so at the side, you just have the fact that tension equals your centripetal force, or equals mv squared over r. So when you're at the side of this motion, there is no component of the weight really affecting anything. So we find that we don't use that as much, but that's just something that's kind of important. If we are somewhere in between here, you're going from adding the weight to slowly getting rid of the weight until you're at the side and you have less and less of it. But basically you don't have to worry about it as much. When you get to the very top, then you still have the tension in the string. So the string is still going to provide a tension that's going to be straight down, because it's always acting towards the center. It actually doesn't matter where you are. This is where the tension is going to be acting, whether it's a string, whether it's you sitting in a roller coaster loop or whatever. But also at the top, you have your weight pointed in that direction. So now, since they're both pointed towards the center, when we come down here and we start writing the centripetal force at the top, we find out that we have tension plus the weight of the object. And so now if I solve this one for tension, we find out that you actually have to take your centripetal force and subtract the weight. So the tension in the string actually still has to provide a centripetal force, but it has the weight helping it out, so it doesn't have to do nearly as much. And then if I replace this with mv squared over r minus mg, this is how we find our tension. We end up with another equation. Looks very similar to the one we did here at the bottom. The only difference is subtraction or addition. Now the weird part is, or one of the things that's additional that's kind of neat at the top, is you've probably been on a roller coaster and you feel like right at the top you're about to fall out of your seat, but you don't quite, or you just barely stay, or you just kind of float a little bit above. What's happening in that case is now your tension is shrinking down close to zero. And so if we do the extreme, in other words, the slowest you can possibly go, your minimum velocity is where the tension actually equals zero. And if that's equaling zero, then it tells me that my mv squared over r would have to equal my m times g coming from this equation down here. If that's true, then the mass of the object doesn't matter. So that's why they don't actually worry about how massive you are. Everybody that would be at the top of that roller coaster would come kind of slipping out of their seats. And we create this equation that I have actually written before. We just wrote it for an object trying to kind of simulate gravity in outer space, where we take the acceleration of gravity and we have to multiply by the radius of your circle. So I'm going to circle this one as well. This v squared equal gr, this v squared equal gr, is actually the situation where it's the minimum speed, the minimum velocity, where you can still make that vertical circle. If you go slower than this, you're not going to make it. And if you go faster than this, you're easily going to make it. So we can find how much tension if you're going faster than that, but this is the slowest you can possibly go. With that information, we have pretty much covered vertical circles. We've covered all the circular motion. We should be ready to finish out the problems, which is what I would like you to do. And we'll come back to circular motion and finish it out with some kind of quiz. Thank you.